University of Illinois at Urbana-Champaign. Obviously a Midwestern boy, I guess a PhD from Michigan, up the road, and very well known in the AI sort of community at NeurIPS and ICML, with interests in significant contributions in reinforcement learning and online learning in general. So I'll leave it to you, Nan.
Yeah, thanks, Sean, for the introduction, and thanks for the organizers for having me here. And today, I want to discuss let's see if I can move this forward. Okay, today I want to discuss and focus on a very standard and basic RL setting where we use a restricted function class to approximate the optimal Q function of the problem. And we can only do so by learning from a batch data set without access to the actual environment. Okay, so what I want is this is a very standard and important scenario for towards real life applications of reinforcement learning. And what I want is a minimal sample complexity result that tells us the conditions under which we can achieve sample efficient learning. And what do I mean by minimal? Well, let's look at the simplest possible sample complexity result in supervised learning, and it goes like this. Right, so we have data sampled IID from a distribution. We have a finite class of prediction functions, one of which accurately predicts y from x. And then it is easy to show that we can learn a near optimal predictor using log f number of samples. And note that I'm omitting the usual pack parameters. And also this result is information theoretic. That is, we assume unbounded amount of computation, and the only bottleneck is the limited sample size, which will be the case like throughout this talk. Okay, so by analogy, I can also try to write down a similar 101 result for batch RL, and it should look like something like this, right? So we have data being state action reward next state tuples generated from the MDP, and this data set needs to be exploratory somehow to provide some coverage over the entire state space. We'll also need to assume that we have a function class, let's say it's finite for now, and which captures Q star, the function we want to learn. And this we'll call the realizability assumption. Okay, so now I can similarly ask, can we achieve polynomial sample complexity in a simple setting where apart from log f, the polynomial can also depend on things like the horizon of the problem and the degree of exploratoriness of the data set and so on and so forth, but not on things like the size of the state space, because we don't want a tabular approach here. Okay, so it turns out that as simple as it looks, this is actually a long-standing open problem in RL. And despite that we didn't know the answer, there were very strong intuitions to believe that sample efficient learning is impossible in this setting, because all existing works hint that realizability seems too weak of a function approximation assumption for batch RL. What I'm going to tell you today is how we obtain a positive result in this setting, thus breaking the conjectured information theoretic hardness. And as usual, this result comes with caveats and limitations, which I'll be talking about later, but still I find this extremely exciting and I want to share with you. Okay, so let's set up the problem a little more formally. As usual, we have the infinite horizon discounted NDPs, where in a trajectory, the learner, the agent, repeatedly observe the current state from a very large state space, chooses an action, obtain a reward, transition to the random next state according to the environment dynamics. And we'll care about policies which are mapping from states to actions. And for each policy, its goodness is measured by this J-pi, the discounted expected return, under some initial state distribution of interest, D0. Okay, and as we are all familiar with, one of the key solution concepts for MDP planning is the Bellman equations, which says that the optimal Q function Q star is the fixed point of the Bellman update operator T. And once we learn Q star, we can simply take the greedy policy of Q star, which will give us the optimal policy. And another familiar concept that will be useful for this talk is the notion of discounted occupancy, d pi as a, which basically tells us that if you run a particular policy pi from the initial state distribution, what kind of states and actions it will visit along the way. Okay, with that standard setup, that's the standard MDP planning setup. But we're here interested in the learning, in particular batch learning setting. So first of all, we'll have a batch data set consisting of SARS prime tuples. And for simplicity, I'm going to assume the very standard offline sampling protocol where state action pairs are drawn from some data distribution mu, and the reward and next state are generated according to the environment dynamics. Okay, so as I mentioned before, this data set, this data distribution mu has to satisfy some exploratoriness conditions. And a very typical standard definition in literature is called this concentrability coefficient, which is a measure. If you want to know what this is roughly about, I've put a standard-ish definition on the screen, but be alerted that this is not going to be the version that I'll be using for our result. And that's related to the caveat of the approach, but I'll discuss that later in the second half of the talk. For now, just accept that there's some parameter C that describes how good the coverage our data set provides over the state space, and the smaller this C, the better. Okay, so and now we have the the usual finite but potentially exponentially large function class that captures Q star, which satisfies realizability. And throughout this talk, whenever I mention an expressivity condition like this, I'm going to use the exact version for simplicity, and we can always handle like small amount of approximation errors, which you can find in the paper. Okay, so this is roughly the setup, and the goal is that we want to find a good approximation of Q star such that it induces a near optimal policy under the initial state distribution. And now we can go back to our earlier, vague informal question and make it slightly more formal now. That is, with all these setup, is it possible at all to achieve a polynomial sample complexity where the polynomial can depend on logarithmic size of the function class, the effective horizon 1/1 minus gamma, the usual pack parameters, and the C parameter that describes the data quality. Okay, and the reason that I said that we had a strong intuitions for this being impossible is because if you look at all existing works in RL, all the papers hint that said that no, we can't do this unless we add additional or stronger function approximation assumptions. And a somewhat typical and representative assumption, which is gaining more attention from the RL theory community recently, is called this no inherent Bellman error assumption, which says that your function class not only needs to capture Q star, but also needs to be closed under the Bellman update operator. You take any function from a function class, make one Bellman update, it still will stay within the function class. Okay. So, the fact that, standard algorithms fail under realizability may be familiar with many of you, but for the purpose to get everyone on the same page, let me briefly go over some popular approaches and see where the failure happens, right? So let's say if you have a batch data set and a function class to approximate Q star, maybe the very first algorithm you can think of is fitted Q iteration, the textbook algorithm for that mimic value iteration by solving a sequence of least square regression problems, right? However, as early as 1996, we already know that fitted Q and basically any ADP algorithms that use one-step bootstrap targets will diverge even with realizable linear class and infinite amount of data, right? So the reason is that even if your function class can represent Q star, it may not be able to represent the ground truth function for each regression problem we care to solve in fitted Q iteration. And an easy fix to the problem is to assume that for any such regression problem we may care about, we can always represent its base output predictor. And that's precisely this definition of no inherent Bellman error, this closure condition that I've mentioned before. Okay, so maybe then you can say, well, this divergence issue is caused by solving the problem iteratively. And one way to avoid it is to minimize a single consistent loss function that doesn't change over time, right? So as long as optimization works properly and we're giving ourselves unbounded computation, so that's not a problem, we should not see any divergence issue. So that leads to this alternative idea of Bellman residual minimization, or BRM, where we try to minimize the violation of Bellman equation, this Bellman error F minus TF, as our loss function. The problem with this approach is that we don't know how to estimate Bellman error straight from batch data. And the naive estimator, which just takes the square of the TD error, runs into this infamous double sampling issue in stochastic environments, that there's an overestimation term shown in the red box. And to resolve this issue, either we need access to a simulator to do double sampling as in Bayes' residual algorithms, which is not possible in the batch learning setting, or we need stronger assumptions and more complicated optimization to account for the overestimation term. And that stronger assumption is precisely a generalization of the closure property that we've seen before. Okay, and apart from ADP and BRM, there are many other approaches that you can think of, and there's a long list to go, but I promise you we've thought about every single one of them and they just don't work. For example, there's some recent interest in some approximate linear programming style methods with nonlinear function approximation to solve batch RL, and we've investigated some of this. And while for the value function class, you only need realized Q star, it turns out that you need additional function approximation to model these so-called density ratios or marginalized importance weights, d pi over mu, because they somehow correspond to the dual variables in linear program of MDPs, right? And you can think of importance sampling, it has its own issues, and et cetera, et cetera. Okay, so one thing that really makes you feel that this problem is impossible is because if you start with this bare bones setting where you're just given a bag of SARS prime tuples and a single function class F, it seems like there's a limited amount of the algorithmic space that's possible is just very limited, right? So the number of different arithmetic operations you can do on these like limited number of symbols seems very limited, and seems that we have already exhausted the algorithmic ideas, or so it seemed. Okay, so with all that set up, it's now I can now tell you how do we resolve this problem. Okay, so we take the hint from a very important old school idea, and I think it's very underappreciated, from the state abstraction or state aggregation literature. Okay, so it turns out that there's this classical result that tells us learning with Q star relevant abstractions is consistent. And what do I mean by that? Well, translating into the language of function space, it basically says that if your function space for representing Q star is not only realizable, but it's also piecewise constant, then we're in good shape. We don't need any other assumptions. Essentially, if you view this from the state abstraction terminologies, essentially what happens is that you're just aggregating state action pairs. You're allowed to aggregate any state action pairs if their Q star values are the same. And if you do aggressive aggregation and control the number of groups you have, then you basically can reduce the complexity of the problem drastically. And then you can basically, for example, solve the problem as if it were a tabular problem, or run Finite-Q on the piecewise function space, whatever you do, okay? And this is consistent, and the sample complexity, vaguely speaking, depends on how many blocks do you have in your piecewise constant function class. Okay, so more formally, you can say something like this, where if I have data that is fully supported on the state action space, then Q star would be the unique fixed point of the projected Bellman update operator, where this TP mu is the combination of first doing a Bellman update, then project back to the piecewise constant function class. And one thing we know is that thanks for the incredible stability of piecewise constant function classes, this TP mu is always a gamma contraction. And for the rest of the talk, it will be also useful to define the empirical version of this TP mu, which is what we actually have access to from data. And this is precisely the operator, the projected Bellman operator that you would use, for example, if you were to run Finite-Q with this piecewise constant function class. Okay, so this is a great theory, but the very first question you should ask is, does a low complexity phi, this abstraction or this partition, always exist? Right, and the concern is because there are many other different types of abstractions where the aggregation criteria is very strict, so that for some large MDPs, you may not even be able to do any kind of aggressive aggregation at all. And if you partition your state action space too finely, you run into generalization error issues. Well, fortunately, this Q star relevant abstraction idea is an extremely, lenient notion. And you can easily show that for any MDP, there always exists a low complexity phi. And the idea is simple, right? So what you need to do basically is just to partition your state action space according to the value of Q star itself. Right, so what I first do here is that I'm first discretizing the output of Q star to some, a finite grid between say 0 and 1. And I can always do that and incur a small amount of discretization error that the theory can totally handle. So I'm going to ignore that in the talk. So that's why from now on, all the Q functions you will see look like these like step functions because I've already discretized their output. And what you do is as I said, you just discretize your state action space accordingly. And note that you can always aggregate all state action pairs, even if they're sort of far apart in the state action space, because we're not actually assuming any kind of topology over the state action space. And you should totally ignore the real access topology in this visualization because that's completely an illusion. Okay. And that's why, like, if you do this, then you're guaranteed that however complex the MDP is, however crazily your Q function like jitters in your state space, lacks smoothness, lacks continuity, I don't care, right? Because I can always get a Q star relevant abstraction of size order 1 over epsilon, where epsilon is the discretization error. So I find this a very neat and cute observation, but I've always thought that it would be totally useless. And why is that? Well, you'd never expect that someone to give you this partition to begin with, right? So you may want to learn that partition in some sense. However, as we see, to construct this partition, we need the knowledge of Q star. But the entire point of batch RL, at least the way we set up the problem, is that eventually we want to learn Q star itself. Right? So this is completely a chicken and egg problem. However, in the next slide, let me show you how to make this observation useful for the problem we're interested in. So recall that our problem is that we have an exponentially large function class f, one of which is Q star, and want to identify that from the batch data. And turns out that you don't need to go to exponentially large f. Even if just f only has 2 functions, this is already a very non-trivial problem and has bothered me for like, I don't know, more than 5 years. But actually, after I realized the solution, I thought, why did I spend 5 years to arrive at this? Okay, but anyway, so the problem is this, right? You have 2 functions, f1 and f2. One of them is Q star, you don't know, but you do want to find that out from data. Right? So here, but now with the previous, the material, I hope it's almost obvious to you how to solve the problem now, right? Because all you need to do is to partition the state action space according to both F1 and F2 simultaneously. Right? So I'm showing you a little bit of visualization here. And again, you just aggregate the state action pairs whenever both functions stay approximately constant within the group of state action pairs that you aggregate together. Okay, and if you do that with the same reasoning as before, you create a partition of the state action space that has a well-controlled size that is 1 over epsilon square, right? And the square is because we're now considering 2 functions instead of 1. Okay, but that's, if all we want is a polynomial guarantee, this is totally affordable. So once you have that, there are many things you can do. One thing you can do, for example, is, we know that the Q star is close to the fixed point of the projected Bellman operator associated with this partition you've created. So then you can basically choose between F1 and F2, choose whichever one that gives you the lower projected Bellman error. Okay, so now that we've solved the problem with 2 functions, let's see if we can extend the idea to an exponentially large f. Well, it turns out that the naive idea of like just creating a partition according to all functions in your function space simultaneously, that obviously doesn't work. because you're chopping your state action space in a super fine, up to super fine resolution, right? So the number of partitions you create is like 1/epsilon to the power of f, which is doubly exponential in what we can afford, because we only want to pay logarithmic dependence on f. Okay, so it turns out like we can still solve that problem, and that brings us to our actual algorithm, which has like a one-line description. So our algorithm is called a batch value function tournament, or BVFT. At a high level, we're inspired by Schaffer tournament for density estimation, and also existing tournament algorithms for model selection in RL. And basically what happens is that you take your exponentially large function space and run the previous procedure on every single pair of functions, okay? And for every single pair of comparison for each candidate function, you record a projected Bellman error, like for a candidate function f, but then you take the worst case projected Bellman error among all such comparisons, which correspond to this inner max over f prime. So note that this f prime is only involved in the objective in terms of creating this partition phi ff prime, and otherwise it doesn't show up anywhere else. Okay, so one concern you may have is, out of f squared total comparisons we make, each comparison produces a partition of their state over the state action space, but a lot of them are just not good at all. And by good, I mean Q star relevant. And you have no guarantee whatsoever coming out of those comparisons. So would that be a concern? Well, for the details, you have to read the proof of the paper. But at a high level, I can tell you that those comparisons basically don't matter at all. And the reason is because if your candidate function f is really good, for example, it's Q star itself, then you realize that among all the comparisons that it is involved in, it is always tested against a good phi, because that phi is always created out of itself. So it's always Q star relevant. On the other hand, if you have a bad f, then among all the comparisons, there is at least one comparison to reveal its deficiency. That is, when this function is compared against the Q star as its competitor. So that's enough to reveal the error. And that's why we take the maximum over all f prime in our algorithm. Okay, so so that's that's basically the algorithm, and a proof sketch for why it is consistent. But ultimately, we want a finite sample bound, right? And it turns out that to obtain the finite sample guarantee, we additionally require two analyses. The first is concentration bound, that all our empirical quantities concentrate around their, the exact versions. There's some technically interesting things in the proof, but I would say overall, if you don't care about tight rates, it's pretty standard. So I just skipped over that. And the second part is what we call error propagation. Right, so note that the projected Bellman error is only a surrogate measure for what we care about. So you have to somehow prove and analyze if the algorithm successfully controls the projected Bellman error, how does that translate to a bound, for example, the difference between the learned function and Q star. And without going into too much technical details, let me just say that error propagation in our case is a little bit non-standard and very different from standard ADP analysis, where in standard analysis, you need to reason about what kind of different distributions you can generate in the true MDP and what's the distribution shift compared to your data distribution. Whereas in our case, we actually need to worry about the kind of distributions you can generate in these mutated, aggregated MDP dynamics. So that's a little bit tricky. Okay, so again, without going into super details, let me just say that we do find that in the literature, there's a version of concentrability coefficient condition that allows us to control error propagation in this case, which is this condition, if you look at this key part from Remy Munoz in 2003. And although this may seem a very stringent condition, let me point out that it actually can be provably satisfiable in MDPs whenever your transition matrix admits a low rank stochastic factorization. And I'll be happy to take some offline questions afterwards. But for now, let's just say if we have this error propagation figured out, then it is relatively straightforward to prove a polynomial sample complexity as shown on the screen. Okay, so before I conclude the talk, I also want to discuss a little bit about the limitations of this approach and some future possibilities. So first of all, as all of you have seen, this approach is clearly computationally intractable for training because we need to enumerate over all pairs of functions. While it is still an open question whether we can make this idea somewhat useful to produce more stable training algorithms, one thing for sure is that this is tractable for another important problem in batch RL, that is holdout validation and model selection. Right, so imagine that you're doing batch RL, you run your favorite algorithms on the training data set, but you're not sure about your neural network architecture or the hyperparameters, so you run many different versions and produce different Q functions. Now, how do you choose between them on the validation data set without having access to the actual environment to do rollouts? Well, BVFT, our algorithm, provides one such answer. And I shall mention that this model selection problem has also been studied for quite some time in the RL literature, but our existing results are comparatively very weak. And I've done some work in that regime and for example, compared to my own work, the current result from BVFT is like substantially stronger by a wide margin in almost every single dimension. And what's more, this algorithm seems actually practical, and we actually have ongoing empirical evaluation for cross-validation in model empirical benchmarks. So another limitation of this work is that we do need to assume very strong data assumption, and it's still an open question whether we can relax the data assumption to the more standard version of concentrability coefficient. And I'll say a little more in the next slide on this. But there's even more challenging problem down the road is, realistic speaking, in real applications, you never expect your data set to be completely exploratory in any sense, right? So you need to be taking care of the deficient support issue of your data set. And but we're just getting started to think about how to do that in our current framework. Okay, so to conclude the talk, I want to give you a little bit of a technical overview of the landscape of finite sample analysis for batch value function approximation. So it turns out that existing works that have, for a long time, have mostly focused on these two cases where we have the concentrability coefficient assumptions and also have this closure property of your function space. But if you look at the analysis a little bit closer, it turns out that you can relax these concentrability coefficient assumptions by first embedding the compared distributions in your function space and compare them from there. Okay, and the nice thing is that if you do that, you have these conditions can be satisfied, for example, in the linear case more easily. Now, the question is really like, what if we really only have realizability, right? And as I mentioned before, I think most of the community strongly believe that this should be impossible. And we have this conjecture in our ISML paper last year under the standard data assumption. And our speculation is roughly like this. It seems like the variations in the data assumptions are minor because with closure condition, they all work equally well, right? So maybe regardless of what condition you assume on the data, like realizability on the function class is just a non-starter. And maybe what you need is really some structural properties of your function class, like it's a linear. Maybe linear functions are easy. And turns out that both of these speculations were totally wrong. Turns out even with realizable linear function class, if you assume the weakest data assumption, it is completely intractable. There's identifiability issues. And on the other hand, as we show in this work, when you have stronger data assumptions, even if you have completely generic unstructured function class, you can derive finite polynomial sample complexity. Okay, So with that, I would like to conclude the talk. This work is with my brilliant PhD student, Tang Xie, and thank you for all, and I'd like to take questions.
Great, great, nice talk. Thank you very much. So there are questions, but I think we're in the same boat as before, that we're just, past 2:30, just the 30-minute mark. So Mingdi, are you there?
Yes.
Yes, did you agree? I think we'll have to just postpone questions for both talks at the end, or?
Okay, yeah, I think we can defer questions till after Yuxiang's talk.
Yeah,
Is that
that
fine?
might be best.
Okay.
Unless there's a quick question, yep, but I don't see. The one here is not quick. Yeah, go on.
Sorry, what?
Well, there is one quick question. Is there anything else, any other function class where you could not have difficulties? Is there anything besides binning where it's tractable?
Sorry, I'm not seeing the chat box.
Well, in the
Is
quick
it in
Q&A,
chat?
well, there's a Q&A, but I'm just trying to paraphrase.
Yeah, no, I see the question from Chaba. I think I have quick answers to his questions. No?
Possibilities, Calico State.
I'm sorry. Actually, I misinterpreted his question. That wasn't a short question. I think we will have to postpone till after.
Okay, sure, no problem. Yeah.
Okay. Yep. Okay.